And so the purpose of this video is to show how you can work with confidence intervals in R and through using RStudio. I do want to focus really on three things, right? So first thing is going to be finding the confidence interval for a mean. Secondly, finding the confidence interval for a proportion. And then finally, looking at how we can calculate a necessary sample size if we know the margin of error that we want. Okay, right, so let's go ahead and get into this. I'm going to start by, I'm going to use R Markdown here, right? So go File, under that menu, though it's not displaying for you, under New File, there's the option for R Markdown. If you click on that, it should bring up this dialog box here. This is going to be this is for me with the course that I'm teaching. It's lab number 4, right? All right, or maybe I'll just call it more generally, this confidence interval lab. There we go. That's nice and generic. Right. In terms of the default and output and all of that, I'm really not that worried about it. Mostly the thing that I like about this is that it will allow me to have the output integrated with the scripting that I'm doing. Right. So let's go ahead and hit OK. And there we are. Right. I'm going to go ahead and minimize the size of the console down here. Oh, is this going to do that for me? Oh, beautiful. OK. It's easier than I was doing. All right, the other thing that I need to do now is I need to have some data to work with. So I'm going to import some data. Right, I'm going to import from Excel. I have an Excel file that I'm going to use. Let's see. All right, so I'm navigating my file system here. Naturally, you would use whatever file you want to. In my case, it's just a simple file here, if I can find it. There it is. So this is a fairly simple file. It just has one column of data in it. You can see it's labeled MPG, right, is the data. So I'm going to name this DF for data frame. That way I can use just kind of a generic code, and the only thing I'm going to have to be specific about is the name of the variable. All right, so I'm going to go ahead and scroll down here and import. Okay, there we go. It came in. Excellent. All right, so back then to my Markdown file. I'm not that worried about making sure that somebody else that uses this Markdown file can necessarily pull the data. I'm not that worried about it. I really just want to have the output there. So I'm not going to bother having the importing of data in the Markdown file itself, though that is something you may want to do if that is something you're worried about. All right, so moving down here, so the first chunk we know, this is all just for setup. I'm not worried about that, so I'll move down to the second chunk. All right, so here I'm not using any cars data. I'm instead going to This is calculating the confidence interval for a mean. There we go. So how do we do this? It turns out it's remarkably simple, just beautifully simple. So, and that is something I don't get to say very often, right? So here we go. We're ready. It's one single line, t.test, right? And then the only thing that you need to put in to the parentheses as an input is your variable, right? So it's going to be in data frame df. Then I put my $sign there, MPG, that is what I want, so I will select that from the list, and that's it. Right? So I'm going to go ahead and run that. So run this chunk, and then it gives me some output here. Right? So first thing I'm going to say, ignore all of this stuff about t, df, p-value, and all of that. That's very relevant if you're doing hypothesis testing. We're not actually doing hypothesis testing, even though that is what this function is designed to do. I don't care about that. What I care about is what's underneath it, where we have the 95% confidence interval. So what this tells me then is that according to my sample, it says right here, sample estimates, the mean is 43.17 according to this, while the 95% confidence interval is 41.10375 to 45.23625. Right, so that range there, 95% confidence indicates we are 95% certain that the true population mean that I'm trying to estimate is somewhere within that range, right? So we say with 95% confidence that the true population mean is between 41.10, I'm just going to round, to 45.24. That's it. So remarkably simple. Now, one thing you might want to do, though, is try different confidence levels, right? So the default here is 95%. 95% is very common. So I'm just going to go ahead and copy and paste this. I'm going to put in a different confidence level, though. So I have comma here. I'm just going to type conf. Oh, right there it is, conf.level. Right? And there we have it. Right, so confident.level, and I put in whatever confidence level I want, but as a decimal. So if I want 99% confidence, I can put that here. Or I'm going to do one more line too, make that 90% confidence. There we go. So then we can compare, right, the different confidence intervals. So we have our 95% confident, it's in this range. 99% confidence, it's in this other range. 90% confident, it's in this different range. Right, so all three of those will be listed here. So the first one, there's 95% confidence. Right. Here's for 99% confidence. Right, so notice it's a little bit wider. Right, and then for 90% confidence, it can go just a little bit narrower. Right, so there's this trade-off here, and that if we want greater confidence, right, we have to give a wider range. And this really is just kind of the logic of when you're trying to guess something. Right? So if I asked you, so how old do you think I am? Right, well, if you tried to guess a specific number, you might be right. But if you give me a range, you're going to be more likely to be right. Right? So if you say, oh, I think you're somewhere between, I don't know, 35 and 45, right, then you might feel somewhat more confident in that. But you should feel even more confident if you say 20 to 60. Right? You can be quite confident, right? Because there are relatively few people who are professors that are under the age of 20, or like over the age of 60. It's somewhat more common on that end, right? But then you start looking at retirement age and that kind of stuff, right? So by widening the range, you can have more confidence, and that's really the way that I think we should think of this, is that you're picking your confidence level. What that's telling you is really a guidance to how wide do I have to go, right? Right. So if I need a lot of confidence, then I need to go really wide to get that confidence. If, on the other hand, I don't need a lot of confidence, then I can go fairly narrow and still get the level of confidence required. Right, so that's a good example here, right, for what the code would look like when you're doing confidence interval for a mean. Like I said, we can ignore the t and the p-value and all of that right now. We don't need that. Right. All right. Now, another thing we can do, okay, I'm not interested in including plots, so I'm just going to delete some of this markdown there, right, is look at what about for a proportion. Right, so this is confidence interval. There is, again, a very, very simple function here, prop.test. Right, so it's calculating, again, it's technically doing a z-test, right? That is a normal, it's a test based on the normal distribution, right? But we can ignore that, right, and focus just on the information about the confidence interval. Right, so the setup here is a little bit different, right, in that you see that the input it's looking for, the first two things, right, are x and n, and then you could also choose the confidence level here if you wish, right. So what x is the number of successes, right, in your observations, right, where n is the total number of observations. Right, so, for example, suppose I'm trying to figure out what proportion of romance book readers would identify as men. Right, would say, yes, I love romance novels and I am also a man, right? What proportion of people fit that bill? So let's say we go out and we ask 100 romance book readers, right? So where'd you classify yourself, right? Man, woman, whatever, right? And 15 of those say, I'm a man. Right? So in that case, our x, that is the number of successes, that is the number of observations that have the trait that we are looking for, was 15. So we found 15 men in our group, and then the second number that we need is what were the total number of people we asked. In this case, it was 100. So there we go. Right. This is all we need. Now we'll automate to a confidence level of 95%, which, let's say that's good enough for us. Okay. And here we go. Right. So it's giving us the data. So 15 out of 100, and then there's our confidence interval, reading very much like everything we had for the mean. So our 95% confidence interval is that we are 95% confident that the proportion lies somewhere between roughly 9% and roughly 24%. Though for this specific sample, the point estimate we have, if we just wanted a single point, it's that 15% based on the sample itself. But remembering this is a sample, we widen out a bit, so we have a little more confidence that the truth is within that range. So we can be, in this case, 95% confident that the truth is within that range. Now that's an important thing to remember, is that if you're only looking at a single value, say that 15% here, right, your confidence level here is going to be 0. Right? Because it's really asking the question of what are the odds that the entire population looks exactly like our sample does, right, on that point. Right? and that'd be exceptionally rare. So it's basically a 0% chance that we're going to hit it. On the other hand, even just throwing in a very, very small amount of confidence that we want is going to widen that, that just a little bit. Okay, so let's actually try that. Right, so I'm going to try, just to make this point, right? That is, if we want a confidence level, let's say that I only want to be a level, I can spell if I try. Right? Say I only want to be 5% sure, right, that the true proportion is within the range that I'm saying. So 0.05, this is an insanely low confidence level. What happens? Well, let's check. All right, so this was the original one, that 9% to 24%. And here, okay, even if we just want to be 5% sure that we're capturing, we need to go from about 14.3% to 15.7%. So we need to have a range here, and that's a margin of error of basically 0.7% or so. Right? They're going around, right, what our estimate is. And so even to be just that little bit confident that we caught the right percentage, we have to have a little bit of a range, just because the odds of being exactly right are so abysmally low. Okay. All right. So I think that I've emphasized that point enough here. So one last task, and this task is by far the most involved, right? And that is figuring out how big a sample size we need if we know what we want our margin of error to be. Right, so this idea of margin of error is really just getting at, say, when I make this confidence interval, I already mentioned this, right? How far away from my sample estimate do I have to go? Right? So in this case, we have our sample estimate was 15%, our confidence interval for 5% was, so it's 15, right, plus or minus that 0.7 percentage points. Right? Or if we went up further, right, so here to be 90% confident, here we had 43.17, and then that margin of error, we could express this confidence interval as 43.17 plus or minus, the number here looks like it's in the neighborhood of 1.7 or 1.6, something like that, right? So something in that neighborhood. Actually, no, I'm off, aren't I? It's closer to 2.6, or 2.7 is about right. All right, so about 2.7 would be how wide we have to go to get 90% confidence, right, based on the data we have. Okay. All right, so sometimes we know what we want that margin of error to be. Like we want to have, say we're doing a customer survey, we're trying to figure out, do you prefer our brand or our competitor's brand? And we want to know within, say, 1 percentage point that we got this correct. Right? Well, in that case, we have a target for our margin of error, that 1 percentage point. Right? So we need to figure out how many people we need to ask, right, in order to hit that 1 percentage point. So let's go ahead and show how we would do this. So first thing I want to do is set up what the formula is going to look like, because there are a number of elements that have to go into this. Right, so in terms of the general formula, let me delete. That's here in our markdown file. It's just pointless. All right, so the formula here, it's actually an inversion of how you would calculate the margin of error itself, and really is what R is doing under the surface with this t-test function. I will say there are other functions here. I believe there is actually a confidence interval function. Let me just check. Right. Okay. Conf.conf.int. That's probably it. Okay, but that's for model parameter. Okay, that's why we don't use that. Okay, got it. Right. So that would be for things like, you know, if you do a regression or something like that, and you want to know, okay, we have this intercept. Well, what's the interval around that intercept to give us some more confidence than just that single point estimate? All right. So for the kind of work we're doing here, t-test I think is probably going to be the easiest way to go. It's very simple. So, all right. But now to get less simple, right? So the formula here that I'm going to introduce, I'm just going to go ahead and write it out just conceptually first. Right? That is n, that is the number of observations we need to gather, is equal to z being a multiplier that we use. Multiply that by the expected standard deviation, divide that by the desired margin of error, and then you square that. Right? So under the surface, if you rearrange this, right, so the margin of error is the thing you've solved for, so it's margin of error equals z times the standard deviation divided by the square root of n. Right? That's how that margin of error is calculated. So z is based, it's normally is actually a t, but we're using z in this case, and z is what we use for, it's a standard normal distribution, which we use for the proportion test. In any case, right, so start with z, and for large samples, z and t are basically the same. So you start with that based on your confidence level, multiply by the standard deviation based on your data, divide by the square root of your sample size. That's how you get the margin of error. So we're just reversing this, right? We need to figure out what the sample size is going to be. We know what the margin of error is that we want, so we just rearranged it. Okay, let's go ahead then, and I'm going to make this R code here. This is R, right, for specifically finding sample size, finding desired, now necessary N for desired margin of error, M-O-E, Mo. All right, there we go. And then I'll go ahead and close that chunk here, and then we'll code inside of it. All right, so we're going to need a number of elements to go into this. So one thing we need is the confidence level that is desired. So I'm just putting conf level and then an assignment operator here. The next thing that we would put here is whatever our desired confidence level is expressed as a decimal. So in my case, I want to make that confidence level, I'm going to go with standard 95%, say. You could change this to 99, 90, whatever it is you want for your specific application. The next line, we then need to take that confidence level and translate it into the z that is going into our formula. So how you do this, right? So it's z, right? And then again the assignment operator, right? We'll take the absolute value of the function here is called q norm, and what q norm does, right? You hand it a percentage value, and then it feeds back what standard normal distribution value, right, would give you that percentage as being the likelihood of being less than this, right? So that is, it sounds kind of convoluted, right? So there we go. We'll just go with it, right? So Q norm is what we're using. So maybe I'll type this in first and then explain it. Right. And then divide this by 2. All right, so it's 1 minus the confidence level divided by 2. So 95% means that we want that center 95% around the mean that we calculate to be part of our confidence interval. Now that means that the two tails total 5%. So our left tail, which is the one we're talking about here, will be 5 divided by 2. All right, so put this all together. 1 minus the confidence level, so that's our 5% that's going to be there. Divide that by 2, that's 2.5%. So this is really asking, say, where does my value need to be, right, such that I have a 2.5% chance of ending up with a value less than this. That is what z is going to do. It turns out this is going to be a negative value, because the standard normal distribution is centered around 0, so to the left is going to be negative. Right? So that's why we take the absolute value here to turn this into a positive number. Now it's not strictly necessary, right? Since we're going to be squaring as well. The square would also get rid of the negative, but I just don't like the negative being there. I'd rather eliminate it from the beginning. Okay. The next thing we need to do is STDEV, that's standard deviation. This is, assignment operator without the typo here. This is just based on whatever you think the standard deviation is going to be. Right, so use your best guess. It's a good idea to guess high, because guessing high is going to end up giving you a little bit larger sample size, right? And you want to make sure that you don't accidentally gather too small a sample to hit the target you have for your margin of error. Now there is a specific case here if you're dealing with proportions, because proportions, the way you calculate a standard deviation for a proportion is actually based on the proportion itself. The formula for that is square root of the proportion times 1 minus the proportion. Right, so you can use this formula if we're dealing with proportions. Right, so let's actually deal with a proportion case and say, I have no idea what this proportion is going to be. Like, I really don't know. Right? So I'm doing something like a political surveying around a very hotly contested election. Right? I really don't know what proportion I'm going to be in favor of one candidate versus the other. Right? So I just have to guess. Well, in that case, my guess, I'm going to make a line previous here, since I'm dealing with proportions, P, I'm going to assign to that 0.5. If you have no idea what the proportion is going to be and you're dealing with proportions, guess 0.5 and calculate the standard deviation based on that. Now, if you're not dealing with proportions, this P line would be, you'd delete that and replace whatever is in the line 37 here, replace that with whatever your best estimate is, right, for the standard deviation for your data if you're dealing with means. Okay. But let's do a proportion case, right, where we have no clue. So we're putting in there P is 0.5, and then allowing the standard deviation line to calculate that. Now if you do the math, it's going to be 0.5 times 0.5, and then you take the square root, so it's 0.5, but you could also do that shortcut. Next thing we need to do is actually calculate the margin of error that we want, except this is something, remember, we're targeting. So we are choosing what we want this to be, right? So let's say that, oh, I want a margin of error of 1%. Since we're dealing with proportions, we need to make this as a decimal, right? So 0.01, that'd be our 1% margin of error we're hoping for. Okay. The last thing then is to finally calculate that n that we want, right? So that n is, and then we put our calculation in. Z times standard deviation divided by margin of error. Right? Take that whole thing and square it. Right, so it's exactly as I have in line 30, the difference here being that I'm using the assignment operator instead of an equal sign. That's the only difference. Okay. The last thing that we need to do, I just keep saying this, right? The last thing we need to do is then display this. Because when you do assignment in R, it typically will not show you the value of the thing assigned. So just to show that, I'm just going to go ahead and run this chunk, and you see here there's no output. None is added at all. So, and we can also see that in the console, no output. Right? Because all of that happens under the surface. So we want it to tell us, right, what is the value for n. The command for that is print. Print n, note this will not send it to your printer, instead it prints to your screen. This is a really old convention, it goes back at least to BASIC, I know. So print here indicating not sending to a physical printer on paper, but rather printing to your screen so you can see that thing. So let's go ahead and run that now. And then we do get the output. So right there is what our n is. So it's basically 9604. One important thing here, typically you will not get an integer here, and it doesn't make any sense to say, oh, I need a sample size of 9,603.647. How do you get 0.647 of an observation? That doesn't make any sense. I'm going to survey 9,603.65 people. So you're going to find 2/3 of a person to survey. Makes no sense. So always round this up. Now you can actually tell R to round it up for you if you wish. There is a function for that, so you can add this if you want to. It's not really necessary because it's not hard for us as human beings to say, oh, this means 9,604, right? But if you really want to, right, ceiling is the name of that function. What ceiling does is it chooses the integer that is above whatever is calculated. Now this does have some things where it might accidentally push you up one more than what is necessary depending on the way that things are calculated inside of the computer. Right? So if something would come to a perfect decimal, sometimes the computer doesn't recognize this and thinks that it's actually rounding something. But being off by 1 is not a big deal when we're dealing with sample sizes this large. So let's just go ahead and run that. Oh, yep, I hit the wrong button. There it is. And you can see, there we go. It rounded it up for us. Great. Okay. Now, the last thing that I want to talk about before I end the video, right, is one of the key assumptions here, right, comes back to that z. And I mentioned the z comes from the standard normal distribution. Now, the standard normal distribution works in a couple cases. One is if we're dealing with proportions and have at least 5 yeses and 5 nos in terms of successes and failures. Right? We have at least 5 observations that have the trait we want and at least 5 that don't. Right? That would be one thing. The normal distribution also, while not technically exactly correct when we're dealing with means much of the time, unless we know for sure what the population standard deviation is, which would be really strange. Right? Technically, we should be using the student's t-distribution in that case. However, once you have a sample size of at least 30 or so, student's t-distribution and the normal distribution look so similar that it's not really worth worrying about. So what that means then is that here we assumed that there was a standard normal distribution. Now for that to be a reasonable enough approximation, we need to make sure we have a sample size of at least 30. So what happens, right, if you plug numbers in here and you get something that isn't at least 30? So you get 24, or you get 15, or something like that. This is possible. There's nothing in the math that would prevent this from happening. Right? Well, in that case, it's very simple. Make your sample size 30. That's it. Right? Or if for some reason 30 is not workable for you, right, just increase the sample size a bit, right, compared to whatever this calculation gives you. And then if you say a sample size of 30 when all you needed was 24 according to this calculation, then what is going to happen is you're going to find you have a margin of error that is smaller than what you were targeting, which isn't really necessarily a bad thing, because that really means you're getting a more precise estimate than what you had previously expected. So gathering a larger sample is typically not a big deal unless each observation is really expensive to get, right? So I will say in practical applications, it would be really rare to find an n less than 30 that you couldn't just bump to 30. All right, so I think that wraps this up. So as you can see, it's not particularly difficult to do, but there are steps involved. If anything, certainly finding the necessary n is the thing that was certainly the most difficult of this. All right, so I think that is it for this video. Thank you for watching. I hope it was helpful.